Hello everyone, I'm Qian Wenxu, Assistant Professor at KTH. It's a great pleasure to be here to present our project, Data-Driven Control and Coordination of Smart Converters for Sustainable Power System using Deep Reinforcement Learning. Moving towards a climate-neutral society, electric power systems are going through a major paradigm shift with the wide integration of distributed energy resources, such as solar PV, wind power, energy storage, electric vehicles, and demand response assets. A key technology here is the power electronic converter that serves as the interface of these distributed sources and loads into the grids. However, this grid transition brings new voltage stability issues that today's grid cannot handle the voltage fluctuations and deviations caused from the high penetration of renewables, which will cause a violation of grid security. Power converter with the distributed energy resources have full controllability that is promising to be utilized to address this challenge. However, it is widely recognized that lack of adequate control mechanism is a key obstacle. Current model-based methods are not able to handle the high volatility and uncertainties of distributed grids. Moreover, optimal coordination of a large number of converters require high communication burden. Our belief is that AI and machine learning will play a key role in improving control methods for converters by making them more adaptive and intelligent to stabilize the complex and changing grids. So the goal of our project is to enable smooth integration of renewables into grids by addressing the voltage control challenge and to advance the systematic design of data-driven control using deep reinforcement learning for environment adaptive, stability guaranteed, and communication efficient grid operation. To achieve this, we first develop an advanced environment of power grid incorporate power converter dynamics. Then, based on the environment, we leverage deep reinforcement learning to train data-driven control policy that is able to adapt to the fast fluctuation of renewable energy sources. Next, a communication efficient control policy is further developed for effective coordination of a large number of converters. Finally, we implement deep reinforcement learning policy on the physical system for the verification. So for details, first, the voltage control problem is formulated as centralized optimization problem, which consists of the physical constraints and objectives. For such a renewable integrated distributed grid with the interface converters, we have two constraints. The first is the power flow constraint, which is represented by these power flow equations. And we also have the power converter constraint to limit the maximum capacity of the output power of converter, and we also have small signal stability constraint. The objective is to minimize the voltage fluctuation of each bus. Then based on the optimization problem, we can formulate the deep reinforcement learning problem as Markov decision model. Then we have an environment and an agent. The agent interacts with the environment, observe the state, and based on the reward to give action for the environment. Here, the reward is to the environment is a grid model with constraints. The agent is the converter, and the action is the reactive power of the converters, and the state is the measurement of power and the voltage. The reward is the objective function. And the centralized deep reinforcement learning algorithm is developed based on this. Then we further develop communication efficient deep reinforcement learning. We divide the grid model into subsystems to reduce the communication requirement and improve the robustness of the control method against the possible sub-attacks. For example, IEEE 33 bus system can be divided into 6 subsystems based on the parameters and the spectral clustering method. Then we develop a multi-agent deep reinforcement learning algorithm that achieves the centralized training and the decentralized implementation. For the training, the actor network of each agent gets the local state and a given action, and the critic network gets the global information of all states and actions. After training, we can get parameters of actor network and the critic network. Then for the implementation, we remove the critic network and implement the actor network for each converter. So in real time, each agent only utilizes the local information to take actions, which enables the decentralized execution. Then we verify this work in a revised HV33 system with 6 PV converters. Here, these are the load profiles and these are the source profiles. Then we feed the data into the training, and here is the training parameters. The right side, the diagram shows the convergence of the training reward. After 5 episode training, the reward is stable. After training, we can get the trained actor networks. Then we test it by feeding random 2 days data. Here is the generated action of each agent. The action is the relative power set point of each converter. And we also show the comparison. If we do not add extra voltage control, the voltage fluctuation is very large at each bus. And even there are many voltage violations in the system. And if the distribution system is controlled with the proposed method, the voltage fluctuation of each bus can be well regulated. We also develop a visualization app that can visualize the power flow and the voltage profile. About the outcome of the project, we have developed an environmental adaptive, stability guaranteed, and communication efficient control algorithm for smart converters to provide the voltage support for sustainable power system, as well as an open source software package to implement the algorithm. This project will provide a cost-effective and flexible solution for renewable integration to minimize the grid stability impact. It will promote the 100% renewable target in the future society. Thank you very much for your listening.